So poker hands are a good tool for learning combinatorics and counting problems for a couple reasons. They allow us to deal with all aspects, both uh, binomial coefficient kind of counting or sample counting, and also with some order counting uh, as well. And also because the answers to a lot of the questions about a basic 5-card poker hand are well known, so you can look them up. But at the end of this video, I'll actually show you a list of all basically the probabilities of the basic hands of a 5-card poker hand. So for us, a standard deck is going to be 52 cards. These cards are divided into 4 suits: hearts, clubs, diamonds, and spades. And each one of those is numbered basically 1 to 13, to keep it simple. All right, where with the aces we'll call 1, the jack we'll call 11, and the 12 we'll call queen, and the 13 we'll call king. Again, usually most games ace is actually highest, but for purposes of what we're doing here, just think 1 through 13 for now. So a card hand is a sample of 5 cards. So how many possible hands that could you be dealt? If you're dealt 5 cards, just 52, choose 5. And that comes out to be 2,598,960 different hands. Now, hands are grouped into like subsets of types of hands, where a type of hand has a certain likelihood of happening, and the more likely a hand is, the less good that hand is, or the less likely a hand is, the better it is. So we'll start with full house. So full house is a sample of 5 cards where you have 2 of one denomination and 3 of another. So for example, you'd have 2 5s and 3 8s. So 5 of hearts, 5 of diamonds, 8 of clubs, 8 of spades, 8 of hearts would be one of those full houses that has 5s, 2 5s, and 3 8s. But the 5 of hearts, 5 of spades, 8 of clubs, 8 of spades, 8 of hearts is also the same kind of full house, but it's a distinct full house from the first one because one of the cards is different. So as long as at least one of the cards is different, it's a different full house that we have to count. So again, we imagine going through the deck of cards and defining a step-by-step process of how we'd have to make a choice to construct a specific full house hand, but always keep track of how many times or how many different ways we could have made that choice. So again, each step of our process is like drawing branches of a tree diagram, and then once we make one of those choices, then we have the next choice, which has to create more branches off of that diagram. Tree diagrams are great when you only have a few branches, but in problems where the numbers of branches are so high, you can't draw them, but you have to imagine them. And that's all the multiplication principle is for counting how many ways you can go down one specific set of choices to create a certain type of end to a process. And then if you add up all the numbers for all the distinct branches that you could have gone down, that gives you the total for the entire process. So again, these answers I'm presenting can be done in lots of different ways. But since we're treating a full house, what our first choice, a natural first choice would be, let's choose 2 of the 13 denominations to be used in the hand. For example, we could have chosen 5s and 8s. After we make that choice, for each of those possible choices, we're going to choose one of those 2 denominations that were chosen to be the card that's going to appear twice in our hand. Once we choose that, the other denomination has to appear 3 times. Now that we've chosen the 2 denominations, and then which one is going to have 2 in our hand and which one's going to have 3 in our hand, we have to choose 2 of the 4 suits of that denomination to have 2 cards, and then we have to choose 3 of the 4 suits from the denomination of 3 cards. So multiplication principle just says 13 choose 2, times 2 choose 1, times 4 choose 2, times 4 choose 3. That gives us 3,744 possible full houses. So again, dividing that number by that number that's 2.5 million or some gives us a probability of getting a full house, which is pretty small. Now let's look at full houses from another way, which is not the best way to do it, but it does illustrate another way of thinking about things. Let's imagine that we actually are dealt the cards one at a time, and we do get a full house. But let's keep track of all the different ways we could have seen those kind of cards coming to us, just in terms of the suits that we're going to, or I'm sorry, in terms of the denominations we're going to see. So I'm going to use the letter A to represent one of the denominations and the letter B to be the other denomination. So A is going to be the denomination we happen to see first. So right now I'm using a tree diagram just to illustrate the different ways we could see the two denominations come to us in order, even though poker hand order doesn't matter. So we can see there's 52 ways, 52 cards we could get, because we can get any of the 52 cards. Could come first. Whatever card we happen to get, we're going to call that denomination A. So if it's fives, fives are A. After we get that first card, the second card could be a B, or it could be another one of the A denominations that we just got. If it's a different denomination, there's 48 possible cards that could be that different denomination, because each denomination has 4 cards. So there are 4. If we got a 5 first, we didn't get one of the other 3 5s. So there's only 48 cards that could come. If we got a 5 and then got another 5, there's only 3 5s left that we could have gotten second card. And we can continue this way. If we got a 5 and then, say, 10, we're going down this branch. After that, we could either get another 5, 3 possibilities there, or we could get another 10, 3 possibilities there. So if we got a 5 and then a 10 and then, say, another 5, after that, we could get either a 10 or a 5. But in this case, there's 3 10s left in the deck that we could get, but there's only 2 5s left that we could get. And notice this branch here, so A, AB, ABA, ABAA, we already have 3 A's of the A denominations. So the next card has to be a B denomination. So there's only one possible branch coming off of this. And then there's 3 possibilities of cards that we could get to get that. So you can just kind of look through this diagram to see all the possibilities. And the multiplication principle says that if we take 52 times 48 times 3 times 2 times 3, that number is going to be the number of different full houses we could be dealt by keeping track of the order of the cards, so that the denominations came to us as A, B, 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 A. But if you look at all these branches, the same 5 numbers appear. There's always a 52, there's always a 48, there's always 2 3s and a 2. So each branch actually has the same number. So what I'm going to call this is the sequence of letters A, B that we see, call that a sequence of the denominations that we see in order. And there's 10 different branches, so 10 mutually exclusive sequences that we would see. But again, each branch, like I said, is just a multiplication of these numbers. So each sequence of order of how we got the denominations, there's 44,928 ways that could happen. That accounts for all possible cards that could make a full house. We're just counting the ways that we could have seen the denominations come to us. So what we'll call these is the ordered full house constructions, where we actually look at the cards as first, second, third, fourth, and fifth. So there's 44,928 full house constructions per sequence of denominations and how they could come to us. So multiplying that by the 10 branches, since they're all the same, there's 449,280 total ordered full house constructions. What that means is we've actually counted 449,280 ways that we can get a full house dealt to us in a different order. So the same full house hand, we've counted a whole bunch of times by rearranging them in the order in which we got them. So what we have to do is divide this number by how many ways the same 5 cards that create a full house could be arranged and how we got them. So again, think about this as given a specific set of 5 cards, A1, A2, A3, for example, B1, B2, where A1, A2, and A3 are of some denomination like a 5, B1 and B2 are some other denomination like a 10. How many ordered full house constructions can be made from those cards? Well, let's think of the process. So pretend I have to have 3 5s and 2 10s. There's 5 choose 2 ways. I could choose the locations in the dealing order to get the 2 of the whatever the BI denomination is. Once I have that, the AIs go in the other 3 places. Then, because the 2 BI cards are the same denomination but of different suits, there's 2 factorial ways of arranging them in the order in which we could have gotten them. So even if they came 2nd and 5th, they could have come 2nd and 5th, or 5th and 2nd, or the cards could have come in the opposite order. I could have gotten the 5 of clubs 2nd, and then the 5 of spades 5th, or I could have gotten the 5 of spades 2nd and the 5 of clubs 5th. Then the other cards, the 3 of the other kind of denomination, could come in 3 factorial different orders. So there's 5 choose 2 times 2 factorial times 3 factorial, or 120 ways to put a single full house into a distinct ordered full house construction based on the order of dealing. Now, if you actually think about that and look at this number, that's exactly the same as 5 factorial, which is just the number of ways of arranging those 5 cards in different orders. So to get the number of full houses, in this case, we take the number of full house constructions and then divide each of those by 120, because the same 5 cards give us 120 different ways of arranging them. So we get the same answer, 3,744 full houses. So again, this is kind of a convoluted way of going about it, but this is a technique to think of in terms of tree diagrams for other problems. It may be helpful. Sometimes it's better to overcount by imposing an order, even when order is not part of the problem, because it makes it easier to count, maybe. In this case, not necessarily, but there are examples when it is. And then you just divide out or group those into groups of the same things or same set of things to reduce it to the right number. So let's look at another type of problem we could see. How many of the 3,744 full houses contain a king? Well, what we're saying is we have to have a full house, but we already know it has to have either 2 kings or 3 kings. So the first thing we do is let's choose one of the 12 other denominations to be the other denomination in the hand. So there's 12 choose one ways that could happen. And then we still have to choose if it's going to be the king or the other denomination. That's going to appear 3 times. That's 2 choose 1. Once we do that, we choose 3 of the 4 of one denomination and 2 of 4 of the other. And again, multiplying those 4 numbers together gives us 576. So there's 576 full houses that have a king in them. So the probability is just that number over the total number of hands. Now again, thinking of conditional probability, what's the conditional probability of having at least 1 king given you have a full house? So knowing that you have a full house, then we ask, out of all full houses, how many of them have a king? Well, it's just 576 over the total number of full houses, 3744. All right, we'll continue in the next video with some more poker hand problems that are a little bit different.